Now, let's learn about how to map textures on spheres. Now, one difference of spheres, one important difference of a sphere from a triangle is that for spheres we use an implicit parametrization. Remember, in triangles, we were using an explicit parametrization. So this explicit parametrization, those UV parameters were specified as part of the model. But the sphere can be implicitly parameterized. This means that for every point P on the sphere, we can compute two parameters. These parameters are theta and phi. And these parameters define with respect to the center of the sphere where this point P is located. Okay? So when we are mapping textures onto a sphere, we don't need the UV values to be given to us. We will compute the UV values ourselves using the implicit parameterization of the sphere. Also, let's associate a coordinate system with our sphere here. This is the center of the sphere. X is along the right, Y goes up, and Z is outside of the board. Okay? Now, these two parameters, let's introduce these parameters. Theta determines how far away, angularly, how far away we are from the North Pole. Okay, so if we are exactly at the North Pole, our theta parameter is going to be 0. And if we go to the South Pole, our theta parameter is going to be pi. Now, the other parameter, phi, determines how far away we are from the x-axis. Okay? So, this angle is known as the azimuthal angle. Phi is known as the azimuthal angle, and theta is known as the elevation angle. Okay, so if our point is on the x-axis, P on the x-axis, our phi is going to be 0. As we go from the x towards the z, it's going to increase, okay? And then as we are on the minus x, when we are on the minus x-axis, it's going to reach the maximum value. It's going to reach pi. Now, after this pi, there are different ways of thinking about it. You can say pi, and then it goes increases and comes back to here, and then it becomes 2 pi. 2 pi and 0 are the same thing. But when we are using texture mapping, we are going to use the trigonometric functions of the libraries that we use, math libraries. And in general, math libraries associate these angles as follows. So this is, if this is 0, this is pi, then when you transition from here, you make one circle and then you transition back, okay? So phi becomes minus pi. And then from minus pi, you go back down to 0. So discontinuity, usually in these math libraries, the discontinuity is introduced here, from pi to minus pi, okay? Instead of having like 2 pi and 0, instead of that discontinuity is introduced here. Now, first of all, let's compute, given an point P, the x, y, z values. Okay? So we are going to derive this from trigonometry. Imagine that this distance is r, which is the radius of our sphere. We can compute x as follows. X is equal to r sin theta, okay? R sin theta is this distance, and then cos phi. Okay, z is similar. Z is equal to r sin theta, this time sin phi, and y is r cos theta. Okay? So, in ray tracing, we know these, right? X, Y, Z, we know. This is the X, Y, Z of the intersection point. Our ray, wherever it may be coming from, has intersected this point. What we want to find are these, theta and phi. Okay, so we must reverse this formula. Okay, so to find theta, theta is easy to find. We can say that theta is equal to inverse cos or arc cos, cos minus 1, y divided by r. Okay, and phi, we can compute the ratio of z over x. If you divide z by x,